the remarkable thing about KRUSTY was we actually nailed it. The test was almost exactly as predicted, which was my hope, right? Go with a simple reactor. We should be able to predict it, and we did.
The gravity of the time is such that every new avenue of peace, no matter how dimly discernible, should be explored. Never before in history has so much hope for so many people been gathered together in a single organization. You will provide a great share of the wisdom, of the courage, and the faith which can bring to this world lasting peace for all nations and happiness and well-being for all men.
David Poston, the chief reactor designer at Los Alamos and the reactor design lead for KRUSTY. Welcome to Titans of Nuclear.
Hey, thanks. I'm super excited to be here. I love talking about this stuff, as you'll see as I go forward.
And I have been looking forward to talking to you for a long time, ever since I heard about the Kilopower project and anything space reactor. I've heard you're the guy to chat with, so I'm glad we could finally get together.
Cool. Sounds great.
Yeah, and so where are you based out of? Do you live around Los Alamos?
Yeah, I live in Los Alamos. I'm in my home in Los Alamos right now. And I've been here for 25 years now. And I came here specifically to try to design space reactors and get reactors into space. So
amazing. So was it nuclear or was it space that kind of started off your career to begin with?
I would say space. I was a mechanical engineer in my undergrad and my master's, and I went to work for General Electric. And thought nuclear is really cool, and nuclear and space go hand in hand in so many ways that it was, as soon as I got the bug of space and nuclear, I knew this is what I wanted to do.
Amazing. So what was the first project you ever worked on?
The first space reactor project I ever worked on was called the SP-100 project, which was a big government effort back in the 80s that actually turned out to be kind of a failure. Well, it was a failure because, the hundreds of millions of dollars were spent and nothing was ever really done. And that's what made me start to think I'm going to go get my PhD in nuclear engineering and come up with ways to do this simpler and easier. And finally, after all this time, we have built and tested the first reactor in the U.S. of a new reactor in 40 years.
Unreal. So, I guess one thing that I've always wondered is, there's only so much information in the public sphere, and I'm not sure everything's declassified. It's just I think a lot of stuff is hard to find. Were you able, when they put you on one of these projects, way back when, were you able to get access to anything that had been tried dating back to the 50s with novel nuclear reactors?
Yeah, everything from the 50s and 60s has been declassified as far as I know, right? I mean, there still could be a level of clearance that something crazy or interesting went on that I don't know about, but I'm pretty sure it's all been declassified. They did all sorts of cool stuff. But the great thing about back then is they could just build and test a reactor and run the test without anybody worried about all the regulations and paperwork. So.
And how come we haven't created, and maybe I'm jumping too far ahead here, but I am curious, how come we haven't created a quote unquote a safe space to do experimental reactor testing where it's okay, here's your plot of land in the desert, or here's your hole, 100 feet underground,
Yes.
Obviously we're not going to give access to just anyone, but if you work for a national lab, yeah, you can do anything you want in this giant hole in the ground or something.
Yeah, and that's the idea. And that we have the Nevada National Security Site, which is the old Nevada test site where they did all the weapons testing. And that's our play area, as you'd say, but it's gotten very hard to do anything nuclear because of all the increasing regulation. That the one thing we took advantage of is the existing facilities they had. We designed our tests really to be operated within what they call their safety authorization basis. and we worked with the regulator, and I can get into that more, how we got through the process. But that is, we have Idaho National Laboratory. There's some desert land that's available, and then of course Nevada, which is the biggest area to test that's remote from the public. But that's the key question. Why hasn't Washington or the powers that be or NASA DOE really set up a place for us to test? And that's probably our biggest lack is a lack of areas to do a lot of cool testing and new concepts.
Yeah, I agree. So what have you been able to do, and like what have you been able to test and pull off over this time?
Yeah, so what we did, we came up with the design for NASA called Kilopower, which is a very compact, lightweight power source to provide 1 to 10 kilowatts of power, which is enough for early human missions and especially for a lot of science missions. And part of that concept is it gave us the ability to test at the device assembly facility on the National Nuclear Security Site in a place called NSERC, which is the National Criticality Experiments Research Center, if I've got that right. And they are able to do, they're the only authorized facility in the US that's up and running to do these kind of tests. Now, they'd never tested what we would call a reactor before. And what would be my reactor is nuclear power is generating heat being transferred to somewhere and making electricity. And so they only take things critical from a nuclear reactor standpoint where we get a sustained nuclear reaction, but don't go beyond that. And we found within their authorization basis, we could run at 5 kilowatts of thermal power for a day or so and learn all we could about how this reactor operated and that it was safe and self-regulating, and get that done within the facility without requiring major infrastructure improvements.
Yep. And so walk me through like the tech side of the project. What's the moderator? What's the fuel? What's the coolant? What's
Yeah. All right, no moderator. I'm kind of famous now for being anti-moderator, and it's only because we don't have the test capabilities. Every moderated reactor has been built and tested before it's been used. And so I'll get into that question later. I won't sidestep your question. That what this reactor is. It's basically a chunk of uranium metal, a highly enriched uranium, about the size of a toilet paper. I mean, a paper towel roll. Toilet paper's on the mind because of the COVID pandemic. Paper towel roll, right? And then it's surrounded by beryllium oxide. And beryllium is the best neutron reflector we have in nature. And so it lets the reactor be very light and small, plus beryllium's pretty light.
And it's the best reflector because unlike other reflectors, which might just, and forgive my layman's terms, might just bounce off a neutron with some probability, beryllium's good because it might absorb the neutron and then shoot off a couple ones. Is that right?
You're thinking of the N2N reaction, I believe, which is a small fraction of it. But in reality, most of the benefit is just it scatters neutrons very, very effectively. And it's got a really high atom density. You take the atom density times the nuclear cross-section, you get a really, really high probability of the neutron being returned. And that's important not just to keep it small, but our whole safety story is based on this. This reactor can't go critical or produce radioactivity unless it's surrounded by this beryllium. So if it falls in the ocean or surrounded by sand or people go up around the cores when they're working with them, there's no way it can go critical. So it makes the whole process very simple to ensure that it's very safe. And that's why the beryllium, not only is it light and gives us a very attractive power system, it increases our safety.
Okay, so just to help me understand this, so what you're saying is if you remove the reflector, the thing from like just looking at it like geometrically and neutronically cannot go critical.
Exactly. Remove it and dunk it in water, surround it by any material you want. Beryllium is the only thing that can scatter back enough neutrons to make it sustain a reaction.
And how come they don't design like commercial electric power reactors with that same like safety principle in mind, where it's like, without a good reflector, you are subcritical, even filled with water. And then, so if anything goes wrong, the reflector, just kind of falls off or something.
Yeah, it's really the low power, because the reactor's got to be pretty small for the reflector to be worth that much. We say worth as in reactivity worth.
Yep.
And if you just have our stack of fuels sitting here on the table, which we did, you could handle, pass it around, whatever. Its K effective is 0.6, which means it's, for every neutron that's lost, 0.6 are made. That's a long way from a critical reaction.
Right.
Incredibly long way.
And you need a 1. A 1 is critical.
Yes.
Yeah.
Yes.
Okay. Okay, so you got your paper towel roll size reactor, and it produces how much heat exactly when critical?
It produces, this test produced 5 kilowatts of thermal power. And then within the fuel, the thermal power is simply conducted through the metal
Yep.
to heat pipes.
Yep.
And the heat pipes are really what you might say the magic of this reactor. A heat pipe is a mechanism that was invented in Los Alamos back in the 60s. And the guys who invented it actually envisioned it being used for this kind of application, but it's been adopted everywhere. Every laptop has heat pipes that cool the CPU, take it to the fan, and Alaska Pipeline has tons of heat pipes are everywhere. But we use the heat pipe to transfer the heat from the core to our power conversion system, which are Stirling engines.
Amazing. And these Stirling engines, obviously I've learned about, I was a mechanical engineer too, and I learned about Stirling engines, and they're so cool in many different ways. But are there commercially available Stirling engines for real industrial purposes at that power level that you can just buy off the shelf?
Yeah, yes and no. There are commercially available engines in a lot of different power levels they're made for home emergency power systems or other applications. There's a 7 kilowatt engine that's out there that's commercially available, but it's not space qualified. And so that would mean we'd have to take it and simulate the launch environments of a rocket, or maybe landing this thing on Mars, and make sure that it can survive that, and other things to make sure it'll operate in the environment of space. NASA's had a big program looking at Stirling engines for radioisotope generators for a while now at the very low power. These are 100, 200 watt engines, which we could use. And they've gone up to about a kilowatt size engine, which are more space qualified, but not really in production. They'd still be kind of pricey until we were able to make a few of them.
And how does the heat pipe part of this work? What's the coolant that moves? So I assume you've got your paper towel roll that's creating heat, and then you've got some outer wall that creates some sort of convection current of some sort. What's the medium that's transferring that heat?
Yeah, so the heat pipes. So again, the fission power is just generated right into the meat of the fuel, the metal, and it just simply conducts to the heat pipe. There's no other thing that has to be done there. Nature takes care of that. And then in the heat pipe, what it's got is in this case liquid metal. It's got sodium inside it.
Cool.
The heat pipes in your laptop would have water. They operate at low temperature. We want to transport heat at a high temperature, because if we're operating in space, we have to have a very high hot end temperature. If you're familiar with Carnot efficiency, we have to reject heat with a radiator, which is hard to do. We don't have a cooling pond. So it has to be high temperature heat transport. And so sodium starts to boil and transports heat, in this case at about 800 degrees C. The heat goes into you heat the heat pipe up to where it's near its saturation temperature. The heat goes into the heat pipe. It boils the sodium down at the core region, which we call the evaporator region, which makes sense. And then you build up vapor pressure. As you get more and more boiling, you get a higher pressure in the core region of the heat pipe. And then the pressure pushes the vapor up to the cold end of the heat pipe where the condenser is, the Stirlings are. It condenses there, gives its energy to the heat pipe wall, which then conducts to the Stirlings. And then the hard part is really a heat pipe will have what's called a capillary wick, or some kind of wicking structure to bring the liquid metal back down to the core if it's not operating gravity. If you have gravity, you can kind of use, it's called a thermal siphon, where just the sodium will fall back down to gravity, like how the top on your pan on the stove might get really hot as water starts to boil, and then it just drips down. Here we have a wicking mechanism that draws the sodium back down. And it's got a very high surface tension, so it works very well.
And you said it's the hard part. Is it hard because that's what's hard to manufacture about it?
Yeah, and hard to manufacture. We're usually talking about a mesh screen of of nickel or another material. Yeah, that has to be a very fine mesh that'll survive the temperatures, and and to test them. One of the hard part is testing them in trying to simulate 0 G for a space reactor. But generally, you can put them on their side, and it's pretty close. But yeah.
And in the core of this reactor, if it's just a giant chunk of metal in the middle, I mean, is your center line temperature a lot hotter than like the outside temperature? Because I can imagine like you've got a higher neutron flux in the very, very center. If your center line temperature increases, if it's hard to like get heat out of that very center of the metal part.
Yes, and so we do develop a temperature gradient to conduct the heat from the inside to the outside. And that's one of the things that limits our power. In this case, we have only about a 20 to 30 degrees Celsius delta T from the inside of the core to the heat pipes because of our relatively low power density. And uranium's a decent conductor of electricity, of thermal heat. So it all works pretty well. Our biggest problem is if we fail a heat pipe, because we want to be redundant. One of the great things about the heat pipe reactor is we can fail a heat pipe and still provide full power. Or if we fail a Stirling engine that's drawing power from that heat pipe or anything, we want to be able to conduct the heat to the adjacent heat pipes so they can still remove it.
Oh,
and that's really what limits our temperatures. In that case, we might get an 80-degree delta T, where we might start getting towards the temperature where we're worried about the fuel getting too hot.
So this almost reminds me more of like batteries and like cells in a battery pack or something more than anything else.
Yeah, it's totally solid state, which is really cool about it.
Do we still call reactors if they operate in like a steady state manner? Do we have like a different name for them, or do we just still call them reactors?
They're reactors, and they're operating in steady state, except most of them are requiring some kind of real-time control system. Kind of like something changes, let's adjust here. They're kind of constantly doing that. Whereas this reactor is so simple, both on the heat transfer and the physics side, the nuclear physics side, that it self-regulates. It totally controls itself. We demonstrated during this test, we never had to move the reactor control at any time unless we wanted to change the temperature.
That's awesome. And how long does it last for?
The core itself is not our problem. So if you've heard of nuclear burnup, like it's how much of a fuel is uranium atoms are burned. Yeah. We usually try to get to 6 to 8 to 10%. Some designs you get more. We burn like 0.1% of our fuel. So in a way, it's a waste of fuel. So the fuel itself would last decades, maybe to centuries at this level.
That's awesome.
And so our lifetime limiter is surely the Stirling engines, and that NASA's got them on test. They're doing reliability testing, but again, that comes back to redundancy. If we make our system redundant into heat pipes and Stirlings, in our first mission, we can either show that they're going to last 10, 15 years, or we'll see what rate they start failing and then have to change our design if we're not getting enough lifetime.
Yeah, I mean, it's a pretty amazing concept, especially for like space or any, sort of, like hard to get to, Arctic exploration, I don't know, where you've just got this, energy source that can produce like consistent heat. Yeah, and even if you have to change out some of the peripherals, you're not shipping fuel in, you're not changing the basic thing that creates heat, it's just there for decades. That's pretty amazing.
Yeah, no, it is. And it is valid to think of it as a battery. It's got unlimited almost amount of energy there, sitting there waiting to be utilized.
Are there any, I'm just spitballing here for a second, because at this low power, you can imagine some sort of other solid state, electrical conversion system, some sort of thermionic or something where it's utilizing, band gaps or I don't know, something. Absolutely.
I mean, that, and all the space reactors that have flown in the past, ours was in 1964, the SNAP 10A reactor, used thermoelectric conversion.
Yeah.
And so it did do exactly what you're saying. So the whole system was steady state.
Yeah.
The problem there really is efficiency. And it comes back to, with the Stirling engine, we can get 25-30% efficiency, our thermal heat converted electricity. With thermoelectrics, it might be 4 or 5, depending on how advanced you get. And so even though the thermoelectric system might be a little bit simpler. This is one case where it would make the reactor a lot more difficult. And that's one of the problems. The conclusions I've come to is we need to make the reactor as simple as we can because we don't have the ability to test it and as much as we'd like to. And it's a lot easier to develop other technologies, Stirling engines, solar panels, heat exchangers. We can do that, build, test, and develop. So my goal is to make the reactor as simple as possible.
Yep.
To actually get something done.
Yeah, amazing. Amazing. Okay, so that's a KRUSTY reactor, right? So anything else that we should know about that one?
Well, KRUSTY was the prototype, of the 1 kilowatt Kilopower reactor.
Okay, yeah. So I'm super excited to hear about the Kilopower also. Yeah, because that's the bigger one,
so,
right?
But they're the same. The KRUSTY test was almost identical to the Kilopower reactor. What was different was how we rejected the heat from the Stirling engines and such.
Okay.
But it was a 100% prototypic test of how the reactor operated, how it started up, how it dealt with transients or failures.
And what's like the biggest that you can scale the system to while still keeping it like the same like principle?
That's a great question too. So along the way, we've kind of decided 1 to 10 kilowatts, we can use our exact technology. With the Stirling engines, you probably want to go to a bigger unit size for Stirlings instead of having 50 small engines. But other than that, identical technology. Then we started looking at if we do have a chance, if we go to low enriched uranium, to get more lifetime out of the core because of fuel swelling possibilities, where we can get like to 20 or 30. So we kind of say our limit is 30 kilowatts with the Kilopower.
Yep.
Now, to me, what's most important is neutronic simplicity and how the reactor operates, because that's the hardest part to test, and you never know if you're building and developing a reactor until you get 4 years down to your test if it's going to work. And so we've designed up to 5 megawatt power systems that use the same physics. We have a few technology changes. We have to change the fuel from uranium metal, UMOLY, to uranium nitride, uranium oxide. And we changed the power conversion system from Stirling to Brayton, gas Brayton, so closed cycle gas Brayton cycle, because it's much more efficient and mass competitive as you go up in power. The Stirling engines almost relatively go up with mass linearly with power, where the Brayton maybe goes up with the square root of power. So once you get above 100 kilowatts, you're much better using a Brayton power conversion system.
Cool. Okay, so you said that you've tested out a 5 megawatt system?
No.
Oh, okay. Yeah.
Sorry. No, we've designed.
Designed it. Okay.
We've designed, and but here's the great thing though. Now that we have KRUSTY, we had the first real data from a new nuclear reactor, anything that looked like this, in 40, 50 years. So, and the remarkable thing about KRUSTY was we actually nailed it. The test was almost exactly as predicted, which was my hope, right? Go with a simple reactor. We should be able to predict it, and we did. And so that's really the most important part of going forward, I think.
Yeah, awesome. So can you tell me about what this evolves into? So you mentioned the other version that you've designed where you switch over to Brayton stuff. Is that the idea to look at future iterations that you might tweak a thing or two here, or what becomes of this?
Yes, and that's a pertinent question. It's a question I always kind of push back on because I like to focus on the first step, right? Get something working, and then how do we go to the next step? Because it's hard to say how. Maybe the second step we definitely have planned out, and the third step we kind of remind, But as you go along, you learn what works and what doesn't, right? So a lot of people spend so much time on looking at these very futuristic systems, which are cool. And I read all the sci-fi. I love it. But I try to keep myself grounded in near-term stuff. So what we have is we're looking at using the Kilopower reactor based on KRUSTY as is to provide, say, 1 kilowatt for a NASA deep space mission, or maybe there's some applications in orbit. Then we look at a 10 to 20 kilowatt lunar lander, which could be very new term. NASA's serious about doing a demonstration, potentially, landing a reactor, say, definitely within a decade. Then the other great use for 10 kilowatts is nuclear electric propulsion. JPL just did a great paper on all the cool things we could do. And basically, we can go around orbit of anything we want to out in the outer solar system. Right now, with chemical rockets, we do these quick flybys. Like we get to see Pluto for an hour or two at close range, and that's great. I mean, that's still awesome that we can do that.
So help me understand why that's possible with these nuclear electric propulsion. Is the idea that if you put something in orbit, that eventually you're gonna lose your orbit and crash into the planet, or it's too hard to break out of orbit if you want to later, and so you need just kind of like a steady trickle of electricity to keep you at the right height? Is that the idea?
Yeah, it's the second one, and it comes down to the rocket equation. If you look at it, really, it boils down to what they call delta V, or how much acceleration your vehicle has. Yeah. It's basically limited once you know how much mass you can launch up Earth on your rocket. And the most important parameter is what we call specific impulse, which is really it really is as simple as just thinking of miles per gallon you're getting from propellant. You can only launch so much mass from Earth. How much thrust or acceleration change can you get from that? And with nuclear electric propulsion, you can get enough to slow yourself down in orbit, maybe then even go to another moon and orbit it. You could go to Enceladus, and then to Europa.
Oh, those are Jupiter moons?
Yeah.
Sweet. Yeah, Jupiter's got a lot of moons. Does Saturn have a lot of moons too, or?
Oh, yeah. Well, Titan is awesome because it's got a thick atmosphere. We love Titan because, people like envisioning helicopters and things flying around. It's easy to land on because it's got a very thick atmosphere. The problem is, well, it's a pro and a con. The bad news is it's methane, which is kind of corrosive. The good news is it's methane, which it can be a fuel. But yeah. And then the other really important moon is Triton, which is Neptune's moon, which people think now might have an ocean and we could get an orbit around that and study it.
Yeah, pretty amazing. Okay, so main purpose is to power orbiting satellites, I guess. And how does the nuclear electric propulsion work differently than the other propulsion?
So nuclear, chemical propulsion is what we do now, right? And the reason that's not very effective is we don't have oxygen. On Earth, we use our cars and we have the oxidizer sitting right there. And that's the heavy part, right? So now when we launch stuff, like the shuttle had hydrogen and oxygen, combined them, but most of the mass was oxygen. So when you go to that, you get an energy density of, I think, about 10 megajoules per kilogram, is really how much energy you get out of it. But most of that is spent, right in the first few minutes of loft. From nuclear power, we can get so much more power. So, it's like, 5 orders of magnitude more energy density in uranium than there is in hydrogen oxygen. So it's an incredible, unlimited amount. We could never dream of using all the power we could get from fission. It's all about engineering. So a nuclear thermal rocket, which I think is where you're going with the question, is one where we run a reactor extremely hot, up to, say 2,500 degrees C, and flow hydrogen through it. It comes out hot, and it's so hot, its exit velocity is such that it gives us much better specific impulse, or miles per gallon, than does chemical, about twice as good.
Wait, and this is getting out of, or is this like on takeoff, or this is once you're already in space?
Yeah, we envisioned in the 60s and 70s using them to get off the Earth, but we've gotten really good at standard rockets, and it wouldn't make sense to use the nuclear one until we were in orbit, and then we use it to shoot ourselves to Mars, and then shoot ourselves back from Mars, is what it'd be used for.
And wait, how come we can't use nuclear reaction? Now, I understand the one where you get something really hot and you flow hydrogen over, and hydrogen is the mass then that you're expelling out to create your momentum. how come we can't like just like break apart and shoot out little bits of nuclear fuel itself? Like, could you imagine some like nuclear gas that we created, where it's actually the fission products that we were blasting out of the reactor with?
Yeah, and that's a concept that's been looked at. It's called direct fission propulsion, I think. Yeah, where you have a very thin fuel element, like a micron or less. I can't remember how thin it is. So, because the mean free path of a fission product, such that it would escape, and then you have an electromagnetic field that takes that fission product and puts it in the right direction. But that's one of those science fiction kind of things that I think we can get to.
Yeah.
But
that's like a really high specific impulse, right? That's like orders of magnitude high.
Insane.
Yeah.
Yeah, for sure. And that's as good as we could get.
Yeah. Cool. Okay, yeah. I mean, it's so funny because I think like space and nuclear, it's just like such a good fit, because of some of the unique attributes of nuclear energy.
Yeah, it is. I mean, especially when you compare it to solar. Solar power is great in orbit, and we probably won't use reactors in orbit very much.
Why not? Why not just get a little reactor, get a little kilopower up there and power the International Space Station, or like?
Yeah, because we, right now the space station has about 100 kilowatts of power with solar panels, and it's not grossly too large. It's working very well. If you're in the sun most of the time, and you don't have a lot of darkness, and you're at about 1 AU from the sun, solar's pretty good. There's 3 places where it's not, and that's where nuclear really plays in. One is on the moon, because the moon has 14 days of darkness. And stuff is going to get incredibly cold. And the ability to store electricity, even if you could make it with the solar over that 14 days, is probably harder than the reactor itself. So the moon is great. Mars is great because it is further out, so solar panels are less effective. And you've got the dust storms, and that we've learned a lot about the dust storms. They reduce the solar insolation, or the amount of heat flux, enough that in order to have a solar farm that would keep a base alive, it's going to be gigantic. I've got some pictures that show it, but it's basically football fields for one kilopower reactor is more than football fields of solar panels. And so it's lighter. It's easier to get there as well, and easier to deploy.
Yeah, I was about to say, like, mass is expensive in space. Like,
yes.
So it's
yeah. So and then the last one, is once you get out past the asteroid belt, and especially past Jupiter, solar power is just becoming less and less efficient, and so you really can't do much fun once you get out into deep space without nuclear power.
Yep, that makes sense. Okay, yeah. So tell me more about where else this evolves into.
Yeah. All right. So what we envision is just scaling up. I think the kilopower technology, or at least philosophy, and the physics, like I said, can take us up to about 5 megawatts of electricity. You're getting pretty serious there. I mean, when we generally talk about human colonization, say of the moon or Mars, you're usually talking about 20 to 30 kilowatts per person. People have a lot of estimates, and I'm not a pro at it, but so you can basically do the math and see that you can how much power you need to support 100 people is 20 megawatts. So it's no, that'd be 1,000 people. I'm sorry, that'd be 1,000 people. So we envision just building up civilizations on the moon and Mars until you get to the point, once you're self-sufficient, which who knows, a century down the road, if everything goes great, that's a century. But if things go at the pace they've gone the last 50 years, that's millennia. Right? But once you're self-sufficient, then we could probably use some stuff there to build our own power plants, right? And maybe just take uranium if we can't find it. So and that kind of coincides with our 5 megawatt reactor, would just barely fit on Elon Musk's Starship, the big heavy reactor, and that's probably as much as we'll ever launch. Maybe we'll build bigger rockets, but until then, we would never be able to take a reactor more than 5 megawatts of size.
Could you take it in pieces? Are there ways that you can break it up and multiple flights, then assemble it when it gets there or something?
Yes, you can. And that's the intermediate point for sure. And I should have brought that up. It's just like, yeah, if you would do, once you got enough infrastructure to maybe do a weld or do something on Mars, then you could do it in pieces.
Yeah. Great. So like, tell me more about like how practically, this happens and some of the, opportunities and challenges, like, working in the lab system, getting from the point of, hey, I've got an idea to, I want to build and test something.
It's very interesting. I mean, the labs are great. Los Alamos, we were able to get it done. It was a little funny the way it all happened. Actually, I had proposed the DUFF test, which was we've talked about KRUSTY, we haven't talked about DUFF and thus The Simpsons. But the DUFF test was what we did in 2012 to basically show NASA we could still do anything. It was like a 10 watt, system that used an existing reactor there. And we just ran it up to power through a heat pipe in it and powered a Stirling engine. In that test, we got to basically with internal money. But the funny story is they'd offered a voluntary retirement at the lab, and I'd offered to take it because I was getting frustrated. We couldn't get anything done. I was going to go try to do it at a university or somewhere else. But the lab came through and said, all right, we'll give you the money. So I stayed, and to this point, everything's been grand.
They must really wanted to keep you. They're like, all right, fine.
Well,
we can keep them.
So that was good. So yeah. And actually, it was very smooth. KRUSTY was incredibly smooth. I think it's because we have a guy, Pat McClure, who was very good at knowing what the regulations were, what needed to be done, and set up and integrated the regulator very quickly and early on. We brought him every step of the way. So the regulator in this case is the DOE. It's not the NRC, as you would think. For application on DOE property, then the DOE is the regulator. And so we set up a program where we set up all these little gates, like we're going to do this and show you that we know what we're doing. We're going to predict the results and we're going to do it and then move forward. Because the difficulty that DOE has and the NRC has is that we're developing all these advanced reactor concepts, but only the people that designed them really have the tools to evaluate them because they're so unique. And what we did with our regulator was, instead of you trying to get the tools to match our predictions, why don't you just let us make our predictions, do really safe, simple, small steps, and if we adequately predicted what happened, then you can tell us it's okay to go on to the next step. I see. And that worked incredibly well.
And how long did that take, and how many people were involved on the DOE side from a regulatory perspective?
The whole process took 3 years.
Okay, it's not terrible.
From us designing the reactor, building it, doing prototyping. We actually did, electrically tested, which is another great thing about the heat pipe reactor. You can use heaters to fool the heat pipes into thinking the core's there, and by changing your electricity level. And so we showed the system worked electrically. We showed the system work with some other simple some tests. And so that was really what got us there. And the regulator, it was usually, and Pat McClure would speak better to this, but we had about, there would be meetings where there'd be 6 or 7 people there. Not all, some would be from the site office, some would be from the contractor that runs the test site, some would be from the facility that would actually do the test. And they were all enthused, because like the rest of us, it'd been 40 years since anything like this had ever been done. So it was a first for everybody. So everybody was really helpful. I mean, a lot of times you think regulator, people get a little squirrely, but in our case, we loved the regulator. They we're probably not supposed to say that, or we're not supposed to be friends, but
now that's a very nuclear way of thinking. Other spaces, like it's a partnership, like you're both there to achieve the same thing.
Yes,
so like
exactly.
Enable safe technologies, whether it's nuclear or transportation or aviation, like it's a partnership. It's not like the regulators are supposed to be evil people. I think like nuclear's kind of got it in its head where it's like the regulator's job is to say no. And and like we have to get past that, and not just on the entrepreneurial side or on the technologist side. The regulator has to get past that too. It's like you can't just say no to everything.
Yeah, exactly. No, that's exactly right. And so it was very refreshing. In this case, the process worked great. we got through it really without any major hiccups at all. In terms of delays, I mean, we'd have to go, well, what if this happens? We'd do a calculation, and there was a lot of technical work involved, but it was a partnership. It was really great.
And what are some of those calculations that you have to prove? Do you have to prove source term release in the case of an accident,
Yes.
that kind of stuff? Is that the main one? As long as you can show, hey, listen, no matter how bad things get, only X number of radionuclides will move X feet and nobody's going to get hurt. Is that like the main thing?
That is the main thing. You got it totally. It sounds like maybe that's your background, but we still had to do calculations to say we couldn't insert reactivity fast enough to cause the core to blow apart or to melt. And so we had a lot of those. In the end, we might have gotten by just saying, look, total source release, we're still okay at the site boundary. But we also did a lot of other things to make them confident.
And I'm curious, what are the tools that you use to show that? How do you predict source term release and the movement of radionuclides through the environment?
Well, I was on the side of producing the source term, which we used the code MCMP, which most nuclear engineers are familiar with, the Monte Carlo code that was written at Los Alamos. And from there we used the code Cinder to get the burnup of the fuel. So here's all the radionuclides you've got. And then from that, you gain a source term. I have another Simpsons code called Maggie that creates a gamma source from that. But then I would send it off to Pat McClure, who knows more about how aerosols are formed and transported out of a building, through a building, and dispersed. But he used the standard, and he used to do a lot of work for the NRC. So he used the standard NRC protocol for that, I believe.
Okay, so got it. So part one is say, hey, we're fissioning, and so we've got these, fission products and some actinides built up that are going to, have this amount of radioactivity, and here's what they are, and here's how long they last, and here's what the amount of radioactivity is. And then that's like the package of information then that you give to Pat. And then Pat says, okay, now assuming that, it is exposed to air or there's some water around or some sodium and it mixes, here's how those, individual atoms or, the aggregate of those atoms, move, through your environment, which might be covered in, concrete or steel or whatever this stuff is. Is that the idea?
That's totally the idea. And another remarkable thing was how good the codes predicted the source term. We had to actually predict how long we would leave KRUSTY on their machine Comet. That's their criticality machine, because they use it for all sorts of important missions. And we couldn't have something that sit there for 2 years and nobody could go in the room, right? So we had to calculate how long till this will be low enough radioactivity so somebody go in the room, which was like the next day, because we had shielded a lot. And how long will it be till we can actually physically take it apart and move it onto a storage cart? And that was a month or two. And then we had how long we'll have to sit on that cart, maybe in the corner of the hallway, until we totally take the thing apart and do like post radiation examination and look at the fuel, look at the heat pipes. And that was all predicted very well with the doses they measured a year or months later were what were predicted.
And the post radiation examination, that happens inside of a hot cell, or are the
because it was so low. It all came together. We tested a 28-hour full test, there were so many things that went into that. Of course, I was going for as much time as I could as the experimenter, but we fit in a ton of transients if we ever talk about the data. But yeah, it was now I forgot my train of thought.
Yeah, it was just not a lot of radiation, or it was well predicted and not a lot of radiation at the end of the day.
Yeah. So you would have the health technician sitting there and measuring, is this safe to handle with gloves? And it'd be yes. So everything had cooled down radioactivity wise, because it was only 5 kilowatts thermal over 28 hours. We didn't generate enough activity. By the time after a year was done, it was meeting the standard handling requirements for a special nuclear material that might have been in a reactor before, that no special require or precautions.
And what are you measuring to validate your initial assumptions? Is it just magnitude of radiation, or are you actually looking at the signature of the radiation as well to isolate individual components of it?
This was just totally magnitude. They were measuring neutron fluxes and gamma doses. Actually, a lot of our data during the test and afterwards was we put dosimeters like that people would wear just all around the room, and then got them measured to see, and they matched what we thought they would.
Cool.
So yeah.
Yeah. Okay, so like, I mean, this is a huge accomplishment. I mean, like, it's still bugged. I'm new to the nuclear industry, or a few years now, but you knew when I came in, not classically trained in it or anything. And it just drove me crazy, reading about the history and like seeing how many different reactors were built of every type and how quickly it happened. And this was all happening like before we had computers or anything, and to see like how much we had accomplished. And then like now then to look at the last 40, 50 years and see how little we accomplished. It's like, this is a big deal that you built a reactor and got it going. So like, does this pave the way now for like the next set of anyone who wants to do experimental reactors to like make it happen?
That's what we hope. And it has. There's been a whole burgeoning of enthusiasm in microreactors and other reactors. I think partially because of this. And my warning to everybody is still to keep it simple, right? Not the simplicity that I talked about for regulation and performance, and not taking too big of a first step. And that, if you really look at what's happened over the dozens of failed programs over the past 50 years, they've probably tried to take too big of a technology step. It's as simple as that, because you have to be able to get done in a certain amount of time, or you're just not going to keep funding. It's got to be a realistic amount of time and money to get something done.
Yeah, these are almost like sprints in agile development for like the software industry, where the whole concept is break things into bite-sized chunks, see where you're at, reset, run the next sprint.
That's totally what we should be doing. But there's still people out there pushing very advanced systems. Oh, we can get this done. Because the problem is, NASA or Department of Defense or whoever wants a reactor, they're going to want good performance, right? And they say, oh, couldn't you give me, 80 kilowatts instead of 30? Couldn't you make this 100 kilograms lighter? And as an engineer, you always kind of want to say, oh, that'd be fun. Let's go for it. And it's like, instead of pushing back, let's do the simple thing. And so I think we always progress. A lot of times I've been on space-directed projects that started off with the simple thing, but as it's evolved, well, we actually need to get this to keep the customer interested, or whatever, and it just evolved that way.
So, as you look out into the commercial reactor space, I think, you really are inspiring a lot of, development, and having that success, is important, beyond the lab system, but into the, private sector as well. What projects do you see that you like, that, you see kind of taking off and that you hope turn into, commercial energy projects, terrestrial maybe?
Yeah, a lot of them are pretty quiet on their technology. I'll have to say, I probably, from what I can tell, Oklo might be the one doing the right thing.
Yeah, I love the Oklo team. They seem to, really be, taking a different mindset and pushing things ahead and having a very aggressive schedule. I love how they're approaching it.
But I think they're using a simpler technology.
Okay.
I last I knew, they were using a technology basically like Kilopower.
Great.
And so that's why I think, I don't really know them personally, whether they, but a lot of the projects, almost every project I see out there now is doing things too complicated. I like NuScale. I think their reactors are the most doable of all the reactors. The question is whether they're going to be efficient enough, or economical, right? So, but I like NuScale because I think they can actually build their reactor for what they say it's going to cost. I guess that would be the two I would say.
Great. And tell me about your your hopes and dreams. If you were czar of nuclear development, and somebody were to come to you and say, hey, listen, we need more nuclear reactors in this country and in this world. You get carte blanche to do whatever you want. What are some of the things that you'd change to really accelerate development in the space overall? I'm saying, your wildest fantasies. What would you want to do?
That's funny. I've gotten so I guess cynical about big projects. That I'd still almost want to take the small steps. I would just say, let's just focus. We need about $150 million to launch and land a reactor on the moon. It's not. But instead, they just keep, putting money into studying all this other stuff. And so, it's kind of been business as usual from on a lot of the government side.
That's so crazy, especially there's tons of other stuff competing for government money in general, but even in the nuclear sector, to see how much money I think is just totally blown on, dealing with spent fuel or dealing, with what they call the nuclear waste issue, even though it's not a hazard to people. Like, why not throw that at advancing space reactor technology? Like, why spend $8 billion on Yucca when we could, create a whole new generation of technologies that make people enthusiastic about nuclear?
Yeah, that's what you'd think. And I should say the $150 million is a KRUSTY-like program, not what I would call a traditional government reactor program, because they get, big. You go to a meeting and there's 60 people there. You can just count the heads and see how much this program's costing. The small team really was why KRUSTY worked. We had basically 4 guys who we talked to each other every day, doing different parts. One was mechanical design, one was the power system, one was the safety, and I was the reactor guy. And we could make decisions like this. We were lucky because NNSA, who was overseeing this with NASA, let us do that. Too often, you have to give your weekly progress reports and sit through these big meetings and get approval for small decisions. And it's not really... The thing is, people will say, "Oh, because that wasn't a real flight system or developed system." It was a real reactor that we built and tested on Earth, which in some ways is harder than testing it on the moon. So you don't need as many people as a lot of programs think.
Oh man, I'm so glad you brought that up. I didn't realize how small the team was, and that makes me even more optimistic.
Well, let me. I mean, there's a ton of people to give credit for that weren't in the small team.
Yeah.
But it was really all the decisions were made by this core team, and then we had help from the safety side and people to help us run the tests and everything.
Yeah. No, unbelievable. Okay. So, we covered a lot today. I'm sure, hopefully at some point past all of this, COVID stuff, we can get together in person. I'd love to see your lab and
cool.
see what you've done and talk more. But, since we only have so much time today, maybe you can wrap up on just a note of, why nuclear is important.
Yeah. I'm going to go to my why space nuclear is important, if that's okay. But nuclear fits on the same thing. I always go to 4 things, right? The first one is curiosity and imagination, right? I mean, why do we want to explore space? I mean, as human beings, curiosity and inspiration are a big part of what makes being a human fun and interesting and worth living. And so I think when we explore space, we're doing that, and we're inspiring people. I was inspired not only by the science fiction I read, but the Apollo program, and you don't look old enough to really have benefited from that inspiration.
Hold on. I've read Dune and all the sequels and the prequels. Foundation series. Right. I'm there. I'm with you.
So that's one. Number 2 is just, science and technology. I mean, that's a spin-off. So I that's one people talk about, if it wasn't for Apollo, we wouldn't have, ice cream and computers, but that's another benefit. The third one is really, gets more philosophical on knowledge. Enlightenment, really. It's like our place in the universe, which we're learning more and more about. The more we explore and discover, the more we can answer some of those questions, which I'm really interested in. So other people might not care as much. But the last one is the one that at least Elon Musk cares about the most. It's really just our viability and sustainability. I mean, we don't know. As human beings, we're incredibly lucky to be here, right? And be conscious. And I think it's our responsibility to, keep that light of consciousness, which might be an Elon Musk quote, alive, and make sure we don't blow this, right? And so one of the best ways as an insurance policy to the human race is to establish colonies on another planet. And right now we have the ability to do that. Who knows where society is going to go, if we're going to progress or stay the same or retract. But I think just from that reason alone is good enough. But I've got 4 reasons that makes me super excited about it.
Awesome. David Poston, thank you so much for your time, and thank you for rejuvenating nuclear excitement and space excitement as well.
Cool. Awesome. No, I enjoyed this. Thanks.
And initiate at least a new approach to the many difficult problems that must be solved in both private and public conversation if the world is to shake off the inertia imposed by fear and is to make positive progress toward peace.